We're going to see the shape function properties now. The shape function properties, as you see in here, are based on some really graphical representation here that allows us to see what's going on with the solution in here. Here's the finite element in this light blue one, and on the dark blue one is the solution phi. Remember, this is the this is a plane where that you have the have an equation of a plane, yeah. But you see here, if you measure the inclination of the plane, or the slope, you may say, of the plane about the x-axis, you're gonna have the d phi dx. If you measure the inclination of this blue plane about with the y-axis, you're gonna have d phi dy. So what I have tried to do here is that if you have this element in here, and I draw a line, parallel to the plane, and then with the horizontal, with the plane down here, and the line, along the plane, or parallel, if you want to say, forms this angle in here, this angle phi. Okay, but we also have a situation where the plane, the solution, forms an angle with the y-axis. So you have a slope along the x-axis and along the y-axis. So if you interpolate the polynomial that we have, the solution is this one. This is the solution of this, yeah. Or I shouldn't say solution, it's the representation of this plane. We can also say that the slope is the gradient in the x direction, but also is the gradient in the y. So you have d phi dx is dn sub I dx times phi sub I plus dn dx phi sub j plus dn dy dx dn z dx phi sub z. So in this case, we know that the derivatives of this shape function are known because we worked out for the example, and dnj dx is b over j over 2a, and dnk dx is bk over 2a. So this is the general expression for the slope of a curve on a plane. Yeah. And Galerkin's style, you see here, that whole algebra is reduced to this simple expression, and then the division for the area here. So what I'm trying to say is that that when you apply Galerkin's method and you calculate the deflection of the inclination of the plane, it becomes easy to predict the plane inclination along on the x-axis and along the y-axis. All right. So we have it here. More conclusions about the shape function properties. B sub I, B sub j, and B sub k are constants because once the nodal values are specified, we know B sub I, B sub j, and B sub k. Phi sub I, phi sub j, and phi sub k are independent of the changes in x and y within the element. Yeah, so it doesn't matter where you are on the plane, the slope is going to be the same. That's all this is saying. So you're not going to have, like in the solution, there's a little ragged part in there. Everything is a plane, and because of that, the changes within the element will always experience a constant value within the element. You said dp dx and dp dy. Constant gradients mean that the small elements are necessary in regions where phi changes rapidly. Well, obviously, if there is a nonlinear system and we don't want a drastic change of a discontinuity, but okay, what else? Constant gradient means small elements. On a discontinuity we will have huge change in slope, but this constant gradient, in this case, it means that small elements are necessary in regions where phi changes rapidly. Okay, since phi varies linearly along its side, and since any line of constant phi is a straight line that intersects two sides of the element. Well, that's the other thing. You see, phi varies linearly along its side from 1 to 0. And since any line or constant phi is a straight line that intersects two sides of the element. That is important because if a level of solution, let's say temperature 25 degrees, would intersect the size of the finite elements that measure 25 degrees as a contour, as a level of the solution. And that's how we draw the coloration on the finite element programs. In other words, what I'm saying is that each gradient, each curve that has certain temperature or certain phi, which could be also stress, will actually produce some boundary by creating the intersection of two elements of 2 points on each finite element. Okay, now let's talk a little bit more about what happens if we do this implementation of the finite element software, finite element theory, and we get the stiffness matrix, the global stiffness matrix first. So let me do this.